All right. So, previously, we spoke about definition of integration. And we have essentially a definition that makes sense. We want to integrate a stochastic process in this space L2 that we talked about against Brownian motion. Remember, of course, this is essentially just a Riemann integral. We also do the type of integral where we insist on choosing the left-hand endpoints. We did this because we showed it as well defined, but also because intuitively it means that this process itself should make sense as a marker. That is, it should be adapted to the process, adapted to the filtration after integration. That's why we chose the left-hand endpoints. So what we want to do today is working with this notion of integration to extend to some sort of calculus. That is, to have some sort of notion of rules for how to manipulate these types of objects. And it turns out the way to do that is to, instead of thinking about this at the level of integrals, to think about this on the level of differentials in some sense. I've said that differentials aren't really defined intrinsically. So we want to say, suppose that x t is a stochastic process satisfying that xt is going to be equal to all right, like this. Xt xs plus the integral from s r of ft dt plus the integral of sr dt.
XR.
Yes. Yeah, I should say that. Thank you. Yes. Some ft, which will be in our level 1 space, and gt, which will be in the level 2 space. Okay. So what am I doing here? I'm just saying that we have a stochastic process that's defined like this. It satisfies this integral equation. So this, of course, should be interpreted as just a regular Riemann integral of potentially a stochastic process. If that is, it doesn't have to be it's in this it's integral. Remember, this just means that the expectation of this integral is finite. And this is the same thing about this. We then say that dx is going to be equal to ft dt plus d over dt. This is a differential equation that intrinsically has no meaning. You can't really understand independently of this integration period this statement. But we write this because our calculus will make sense in the intuitive heuristic way that it looks like a series of laws that we are used to defining for differentials, derivatives, chain rule, product rule. But whenever we write an expression like this, we need to understand this to mean that x satisfies this equation. Okay. All right. The point of today really is work out the lemma, which is really a shape one. If you want to know why we call it lemma, the best answer I can come up with is because there is an Ito theorem, which has nothing to do with any of what we're talking about here. But yeah, I just think it's a chain rule. So the statement, or chain rule, is. So go ahead and suppose that satisfies that same derivative equation. And go ahead and define stochastic product of y t equal to u of x t, where u is going to be, I'll write C2, just to be a little bit simple. But what I really need is that it has two derivatives in the first component and one derivative in the second component. Okay, so I'll just say now, write this, where ux. Right, so we have two derivatives in our space variable and one derivative in our time variable. Eta lua then tells us then t y c. Well, think about this. This should be a chain rule, right? So we should be expecting to take time and space derivatives in this, multiplying them by some sort of differential determined by these. So we would expect to have something like ux. I'll omit the independent variables. X t plus u t t, right? This is what you would expect. It's not quite true. Plus 1/2 u xx tt squared. We can write these a little bit more cleanly as plus ux t plus 1/2 u xx squared plus ux. So, okay. Going from the first line to the second line is just writing out what the xt is standing back here. So nothing special there. But the thing that is different is this term here. You can call this correction term if you like. But the point is that our usual chain rule for derivatives in the standard calculus would tell us that we should have this expression here. So it's surprising that somehow we're getting a second order term showing up in this derivative. Does the expression make sense? Does the statement make sense?
Yes, but do you have an idea on how we can visualize it like that?
I don't know if I can give you an idea of how to visualize this, but I can give you a justification on the little Taylor series. They'll give you something. And it also lends credence to this heuristic that I mentioned last week. So I give you that. I don't know about visualization. This is a little harder.
Yeah, because I mean, if you say that it's a correction term, then sometimes it's possible to have a geometric idea. Sure, not always, of course.
There is. I'll make this statement. The fact that this appears in the Ito calculus is the reason that when we do differential stochastic geometry, that we insist, whenever possible, on using the Stochastic general, because this term does not appear in a Stratanovich calculus. So, this precisely the fact that it's hard to give a geometric meaning to this, it's not very clear, is why we need this. I mean, the existence of this term is also equivalent to what we'll see a little bit later, that somehow an integration by parts formula also has a correction term that doesn't sit well. And the integration by parts is what we usually need to be able to do on tangent spaces. So from a geometric perspective, there's something wrong about this. Yeah, I can write out. So why is this happening? Well, this is very much a heuristic argument. Please don't take this as concrete. But if let's say I have u of x, I can say that this is somehow u of 0 plus u prime of 0 x plus 1/2 double normal squared. So assuming it's analytic, or at least C2, we can say that's range to tailor kind of around 0. So we can say something to the effect of then du of x should somehow, well, I mean, this term is absorbed into this derivative. 1/2 double prime squared. Yes? Something roughly to this effect. Well, if you actually write this out and compare these term by term, this, of course, just this guy here, hash, use more than both of these. And I mean, I only wrote this in a spatial variable, via the time variable, you have this time term here. But our correction term, second derivative of x, is coming right here. What this effectively tells us is d of dt squared, that is square different to whatever this means, is somehow already equal to let's solve for if you want to be slightly more concrete, slightly more sensible, you recall that we talked about the quadratic variation of Brownian motion. That was that the one variation of Brownian motion is always 0, and this quadratic variation would be finite. It would always equal the length of the path. This is the same statement, actually. This equality can be understood in the sense that quadratic variation of Brownian motion can be integrated to give you the path. Okay? And this, again, heuristic notion is exactly where that's coming from. I do actually want us to have this expression because it turns out that, remember, I'm saying whenever we're working with these stochastic differential equations, there's somehow a formal, right? When we work with them a little bit later, it turns out that when we have terms of this sort that show up, if we replace them with the dt, we get the correct answer. So we'll want to have this heuristic in mind. All right. Anyways, let's actually go ahead and try to prove beta 1. But to get there, we're going to do this.
Once again, we saw this property before.
Yes.
That the second variation.
We should say quadratic variation, yeah. Because second variation.
No, second variation, whatever. It's puzzle ways. But that's what we had. And then you just collect the first order terms.
Yes.
In D1. And there is dt, first order terms, and dx.
Yeah. So what you could do if you wanted, and what a lot of the introductory texts actually do, is to make this statement. They literally just write out the Taylor series for this function u in 2 variables. And what ends up happening is that you have terms dt, okay, which was fine, just like this. You have terms dx, okay, fine, like this. And then you have terms dw squared, dw dt, and dt squared. In the classical theory, dt squared goes to 0 faster than dt, and so in some sense this disappears. And same thing with dw dt. This term goes to 0 faster than dt, so again, this term disappears. But the interesting thing is that at the level of integrals, the rate at which this type of term converges to 0 and the rate at which this type of term converges to 0 is the same. That's really what this is saying. And the point you make about 2 variation versus quadratic variation, the fact that there's this subtlety here at all is the reason that I have to insist that this is a heuristic. Because these types of expressions only make sense when interpreted at the level of Ito integration. I didn't write this, which we know that Ito integration is defined using these partitions whose dimension goes to 0, which is why quadratic variation is the correct thing to use, not 2 variation. Yeah, so this becomes sensible as soon as we insist that this statement is interpreted at the level of Ito integrals. That's really the conclusion. But you don't want to say this abstractly, because there's
I
other.
understand. This is coming from construction of people and not coming from construction of the certain knowledge due to the choice of the point.
Exactly. Or if you choose any other integration theory, you could, have quadratic duration terms, and they're not sensible, or they have to be interpreted differently. So this statement should be considered sensible as long as we interpret this as a theory.
Oh, this is fine. We can make it into rough path.
Yeah. This whole other theory of integration, the rough paths theory, which of course this statement is not correct.
Yeah, it means that you said the square is 0. If you want to define the integral, you should also take care of the terms of the form. So you have sum of f of xi plus 1 minus xi, and that's the definition of the integral. But if you do properly, you also have sum of f of xi multiplied by xi plus 1 minus xi squared. Right? And this you can show that is 0. But if you put ground motion, this particular integral is not 0, and then it's 0. So you just get one additional term, and that's why it's annoying. Anyway, sorry.
So the point now for the next little bit is going to be prove this. We'll need to work in a number of steps. So first, we need a symbol clump. This is 11 on the proper sense. Yeah, I keep saying we call this 11. Bothers me. This should be the level of the growth. So this is a very important statement, but it's just the name that gets stuck to it. So, but an actual 11 now. First, I take differential squared. Yeah. Look at that. I can do it. And this equal. Okay. So I want to prove both of these without having any other theory about interpret. I don't want to be able to use this sort of shading when I want to have these expressions on their own. It turns out there needs to be a sensible proof. One of these we've already proved. So to see this, one follows from the fact that the integral t. Recall that we actually computed this explicitly when we were trying to understand what it meant integrating with Brownian motion. So I should write 0 to r here is equal to 3r squared over 2 minus 1/2. Do you see this? Because if you take this statement, first of all, we agree, right, that I proved this last one. You take this statement, you move it to the level of differentials. We just have that WT to alpha WT squared minus which then, of course, is the same thing as W number 1. All right. So the second one that we need to prove is number 2, and we're actually going to prove this essentially by I mean, we're going to write out these 2 expressions, sum them, and we'll see what this is. So, so if I take these 2 as the first, their interval from 0 to r of t. This is, by definition, the limit as n goes to infinity, whatever, of the sum from k 0 to the h r. So I was saying that's fine. Of plus 1 n w t n. I need the k here, not k plus 1 there. Plus 1 WTN. Right. Over sequence of partitions. Yeah. This mesh size going 0. Right. Okay with this? So this is just by definition. And of course, it's essential here because we're using feet of integration. This is TK. It's the left-hand endpoint. Whatever our sequence of partition is. The integral from 0 to R of T. Well, this is going to have a remarkably similar expression, right? 0 size partition 1 star. Where we can use the same partition or another partition, it doesn't matter, right? Because the point is that we have to have some partition that goes to 0. The key thing to observe, though, is that this is a Riemann integral. Not even Riemann solutions, we're just integrating against dt, right? So this, the sample point, I put a star here. Because you can choose any sample point in the interval. Emphasize this, way too many times. So what we do, we choose Cn star to be the right endpoint. Okay? It's just a choice. A choice shouldn't matter. I'm choosing the right endpoints. If we then sum these two expressions, we have the integral from 0 to R of T plus 0 over 0 to R of W is equal to limit that goes to infinity across our partition. Y equals 0, the size of the partition. What happens? Well, this here being tk plus 1 means that this term right here and this term right here cancel. Yes? Mm-hmm. So we get, let me write this properly, W tk plus 1 CK. The k plus 1 there, right? Yeah, it should be k plus 1 because we're keeping this term. And no, that's the one to cancel. Sorry. This term. So we have minus this one and plus this one. It should be tk. Yes. Right here. Minus the same thing there. So minus tk and tk. Yeah. Yeah. So this is telescopic. Cancels. And of course, we end. Because this is almost really 0, it's 0. It's the and we investigate this by taking this to the level of differentials. You take a diesel, that's the left hand side integral just disappear, the right hand side, we get the differential of this. Okay, so it's neither of these statements are too rough to show, but really all of this is following directly from writing an explicit expression here. We can use these now not to make a chain rule, but to make a product rule. So this is often called the formula. Yeah, again, don't provide formula. Why not talking about it? So we go ahead and suppose that the I'll use 1 and 2 here, but this should not, of course, not be interpreted in all of that. Right, so we know that 2 stochastic processes that are understandable. Right. Then we want to have an expression for the differential product. We get what we expect, right? 2t plus 2t 1t. Then naturally there's going to be some sort of correction. Plus g1t, g2t. So, of course, once we have the lemma, we'll be able to prove this pretty straightforwardly, right? By writing this out as where multiplying it together is somehow our function. But how do we see this? The level we currently have it? Well, this is exactly what our classical product rule would tell us. This comes when you take the expansion of thinking of this as some sort of Taylor series, that the product of these two terms will be G1t, G2t, dwt squared, which again, dwt squared acts as dt. That heuristic that I mentioned before. Right? Questions on the statement? Is this okay? Okay. So, yeah, I'll mention, by the way, suppose, do we just do one of them or both of them? Yeah. Yeah, actually, consider this in level intervals. So, I'm sorry.
This term dt
Yeah.
also being by the same reason.
Yes. Yeah.
Square of this.
Yep. And it's a fundamental rule. In any of these expressions, you expect to get exactly what you would from classical calculus, plus a correction term that is always exactly equal to, it always arises from considering dwt squared as dt.
For the ego.
Yes, yeah, in the ego calculus. Yes. Okay. All right. I want to write this out. Level of integration. What happens when you write a product rule and integration level? It's integration by parts, right? It's not surprising. So we have something like this. Integral from 0 to r of x2t d x1 t equal to x1 r x2 r minus x1 0 x2 0. Okay. Right. Minus our integral from 0 to r. The order changed. So x1 t 2 t. Right. Here's the regular integration by parts. And of course, we're going to have integral from 0 to r of g1 t. So, integration by parts work, great. I'd like you to observe if either, if either G1 or G2 is not a stochastic process, but rather just, I'll just say it's exactly identically equal to 0, then the correction term vanishes. We get this classical formula, which is exactly the integration of parts formula that we had to visit the PWs paleobinary sigma integral, which I was insisting when we defined that should we have something deterministic, our integral must satisfy that integration compartments formula that came from the paleobinary sigma integral, right? So this verifies that. We have either G1 or G2 we verify the integration by parts formula that we expect from PwC. All right. And yeah, I said this a couple times, but the fact that this correction term doesn't appear in Stepanovich integrals is exactly why we tend to work with Stepanovich integrals in geometric. Well, let's talk about a proof. Proof's not that bad. Of course, the proof is going to follow from some sort of approximation argument, right? What else do we do? But let's begin. So first, that's I need F1, F2, G1, and G2 are independent of time. So what I mean by this is that they're random variables. They're still random in this sense, but the random variable does not change in time. So it's not really a stochastic process, or you would say a time constant stochastic process, right? And just to make things simple, we'll say that x1, 0 equals x2, 0 equals 0. You can do this almost shortly if you like. All right. So we're working with this much simpler expression first to actually get the result. So what this tells us then, we're assuming this, right? But since F and G time independent, I'll figure out what this actually means. And X1 of T, yeah, it's literally just F1 times time plus you just integrate those expressions. So these differential expressions can be integrated directly because everything is constant, essentially. Or replace the one with I, because of course this is true as well. So we take the expression that we actually want to have here. So this is integral from 0 to R times x1 t dx. Plus, probably a little bit lazy and write one integral sign, even though these are basically separate integrals. Okay, so if we have this expression, we can expand it out very explicitly now, right? I mean, ahead of time, we already knew how to understand the differential. I'll write that first. So we're going to have an integral 0 to R of x2t. Let me regroup things really nicely right away. Yeah, I don't want to write all this stuff out. So this is what I'll say. First, you understand that we're integrating against expressions dx1 and dx2, which necessarily have this form. So we expand that out. Also, because of our assumptions, we have explicit expressions for these integrants. You write all of this out. And fine, I'll write it at this level. We have the integral from 0 to R of f1 t plus g1 t t 2 t plus f2 t plus 2 t. All of this should be dt. All right. So these are all our dt terms essentially. Plus integral r, which should be f1 t g1 t w t g2 t. I mean, the integrand is very similar, right? Because this is just coming from the expansion of x2 and x1, but term after different G1T, because this is the iteration of the dw. WT plus at the end, we get a G1, G2 term. All right, yeah. G1R, G2R. And this comes from the actual expression carrying out this GT here. Maybe I write it like this. Interval G1T, G2, T, 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 R. Yeah. Okay. So if we regroup these terms, of course, literally erasing the expression I was trying to say for this moment. That's all right. The expression here is what's going to actually make this interval, or this interval reprehensible, right? Because if we regroup these, we're able to get F1 R equal R squared. We see this term, yeah? From integrating out this plus G1, yeah, those are G1R F2R plus G2R F1R integral from 0 to R equal these. So we'll get TWT plus WT T. So this comes from the second terms in here and the first term in plus 2 G1R G2R integral from 0 to R. So this comes from the remaining terms in the second integral, or yeah, second integral, whatever it is, and then the last integral. Just that. All right. Cool. So all I've really done was assume some nice, assume everything here is going to have stochastic process constant. Played with the actual definitions, the definitions and the fact that we can explicitly compute xi in this case. And we get this expression. But our lemma that was earlier right here tells us that we know this integral and we know this integral, this expression better. So we write it out. We get, of course, F2R squared final plus G1R F2R plus G2R F2R times this expression here, right? Which, yeah, R. This was our second. And then 2 here plus G1R, G2R, so where am I getting that from? That's this plus this. These two together with that second term, essentially. Yeah. I can rewrite it like this. Let me factor the G1, G2 out. So place this G1R, G2R, and then transition here to here. That's there. Now it's in the exact form that I have in Nova. The lemma said that on the level of differentials, this expression would be W squared. Yeah, but that's it. If you actually compare this now, take this at the level of differentials and this is exactly what the right meant. Because this is 1 bar. Not that exciting. I mean, it's interesting though because we're playing around with integrals, just expanding out these group definitions, and that's about it. I mean, we needed to have these two explicitly computed, but beyond that, it's really just symbolic identification. It's like, Okay, so what do we do for the rest? Well, the first, or the second step is, of course, if F1, E1 are step processes, everything's going to stay. You carry out literally the exact same expression where you sum over the steps. So you'll break these integrals up into some parts of partition and everything carries over it. So there's nothing special there. But now we have, this means that we have this result for step processes. And all that's left is an approximation argument. I mean, what you can do, I guess I need to say it, is that in general, so for general Fi in 1 and Fi 2, we choose step, choose a sequence. This is step processes. So then we have convergence. We want the value of the integral from R and should be finite, right? Yeah. 0 and 0 R. Right, you have step processes, so we have convergence essentially in L1 with the F's, convergence in L2 with the G's. When you do this, you define the integrals as limits, and everything converges eventually. Cool. Yes. Perfect. Take a break, and when we come back, we will use this to prove the E to O chain rule and actually see a use for this. So, we'd like to now prove the chain rule. We will use, of course, the product rule that I just written up, which is an interesting way to do it, I think. Anyways, so yes. What we'll do is build this up from polynomials first. So first, let's take x, if you like, to x to the n. So for something fixed, x1 n. We want to prove, to show, of course, that d u t, according to our rule, is supposed to be ut plus ux plus 1/2 ux x. So here we have this f and g, but they're not going to be present. So we're going to take just so in which case this go away because there's no t. We're going to have in total, let me just write that. Mx minus 1 dt is what we expect from the derivative plus this second order term, which is n minus 1 x to the n minus 2 t. Yes. Oh. Okay. This is again an example of looking at this and saying, all right, we would expect this. This is something coming from dWt squared. Do bear in mind that contrary to the previous notation, m is an exponent, not different variables. So m equals 0 is obvious. 1 is literally a tautology, and 2 is actually from the one that we had before. So we proceed by induction. So assume for induction that we have dx to m minus 1 is m minus 1 x minus 2 t dxt plus 1/2 m minus 1 m minus 2 m minus 3. Right. I'm wondering if it would be worth it to actually put the g in there. Yeah, why not? So none of this is going to get more complicated with it. So I'm going to go ahead and write. Because in that case, what changes? I mean, the only thing that should appear is the g in this. Right? F is in here, but it's in this direction. So we assume and then we use the product rule, right? So dx and of course dxt times minus 1t. We get xt d x minus 1t plus d xt plus our correction term, which in this case, it has the extra minus 1 x first, then g squared, right? So this is us using our product. Yes. So, well, we now use our inductive assumption right here and expand this out. We're going to have m minus 1, I'll write it, m minus 3t, g Okay. So then what happens here? It's just algebraic rearrangement. We need the simple expression that is obvious, but nice to write. M minus 1 plus 1/2 m minus 1 m minus 2 is 1/2 m minus 1. Clearly, right? So we use that to combine this term. Oh, wait a second. It bothers me. There's a squared distance somewhere. Oh. Thank you. Okay, we combine this term with this term, right? And we get this expression. It's all exactly what we'd expect. And here we have m minus 1 equals. And we get the result. dx t. Here, we're going to have our m x m minus 1. Here is this m minus 1 x. it's not that surprising. But the point is that it's basically an algebraic argument combined with one simple inductive step. Really was necessary, again, to have this 2 case. So it was important that we had that level number 4. But beyond that, it's all pretty straightforward. All right, next, think about it. The D operator is linear. So the fact that we have this for expressions of the form x to the f means that we have it for all polynomials in x. Yeah. So 2 D linear implies that u of x in x is done. Now 3, then let u of x t, f of x, g of t, where f and g are both
just a similar thing.
yes.
There's a mismatch with the powers. When you add the g squared terms. X, then you get the 2 minus 2, right?
Which it should be.
Yes, and then one roll that you add to it is minus 1.
Did I write this wrong?
I think maybe it should be.
Yeah, I did. Yeah, when you use you should be using the power on this, so this should be equal to
Minus 2, right?
I understand.
Okay, then I-
That should be, I understand. Thank you. Yes, good catch. yeah, that is me writing it wrong. Okay, well, so polynomials in x. Now we want to do polynomials in both. Okay, so du is clearly df. That's what you like, and just g plus f of x gt, right? Okay, I'm just using the simple product rule for polynomials, something magical happening here. So that when we actually take this at the level of differentials, we du of x. So when we take df here, we're going to wind up with, right this way. We wind up with because we have we applied the actual rule that we just proved here for polynomials, and it just looks like xt so that's this plus, of course, we have this guy, xt, right? So, I mean, all I'm really doing in this is saying that if it's a product of this form, that this expression, of course, is perfectly normal because there's nothing stochastic going on there at all. I mean, and then here we just use the product rule that I just proved, polynomials. So the end result is exactly what we want, right? Because this is the expression we would expect, that we're expecting. I don't know. It looks gross, but there's not really anything else to say there. So at this level, what I have is that if I have a product of polynomials, it's fine. Expand this one step further. Again, the linearity. This works for you. Any polynomial within x, right? Any polynomial of 2 variables we have. We're just taking sums of expressions in this form. And then the last step is the standard approximation argument. So what you need, I'll say this properly. So for arbitrary u that is c2 x c t. We can find a sequence of polynomials such that un is reduced to u, x1, x, x1, xx, and u, n is reduced to c, where we're doing this uniformly on compact subsets of R cross 0 R. Right? Right, the density of polynomials in this kind of this sort of space. Something special. So we take this sequence of polynomials. Anything more special about it? Not really. Okay. I mean, I'll write the expression, right? We know that for any polynomial in the sequence, we're just going to have un 0 R and plus t half uxx squared plus R plus R u x g. Right. I mean, it's technically what I've already proved. We just have this for any polynomial. We take our limits as things goes to infinity, and everything holds in L2. That's all it is. Okay. So it's a little dissatisfying, I feel. The interesting step, again, is somehow captured just in the fact that we can make those expressions for polynomials. We're making just argument for density of polynomials in this general space. Yeah? Okay. All right. So what we get from this, though, we now have a way to actually make sense of stochastic expressions. So I want to give a nice little application of this because I think it's a nice example. So what I want I would really like to find a stochastic process. This is an example of using these rules to accomplish something other than enjoying as they exist. T such that differential of yt is equal to itself. And for the fundamental, it's a little so what is this accomplish? This is effectively trying to look at the exponential distribution, right? Because classically, if these weren't stochastic processes, we'd be looking at some function df dt is equal to f, something like this. This is what we're generalizing here. So we could take it on something straight guess. We would guess that it should be exponential, right? E to the y. Of course, it's not. I think at the end actually hinted this one quite earlier, some other. But what do we do? Well, we apply the chain rule. to the expression ln yt. Okay, why am I doing this? I want to apply the chain rule to this because I think it should be exponential based on my intuition from classical. So the ln of this should have its expression, right? So if we're going to use chain rule, we should take a derivative of ln of 1 over yt t plus, and then we should be taking us 1/2 our second derivative of this. So we should have negative 1 over yt squared. Yeah, I did it right. Yes? I feel like I'm making a little silly about this. I always hesitate when I do these sort of expressions.
Sorry.
No, it's fine. Yeah. Oh, I know what I did. Okay, yeah, it's fine. All right. So we get this, right? And
Oh wait, so then that's
yeah, I don't know why I'm. No, the lambda shows up in here. This is fine.
But on the other part, lambda y, so like it's lambda y to 35.
Yeah, I did this ahead of time, and it was a mess that time as well.
No, you just have to write the lambda y to
Yeah, that was.
then you square lambda y. So you
Yeah, sure. Also.
Is this
Why is my DWT not showing up? Yeah, this is okay. Here we go. Okay. Yeah. Okay. This is what I'm expecting to show up here. This is fine. Okay. Up to the fact that all right. At any rate, the point is when you actually write this out, yeah, this here is dyt will have us have then the wt right minus 1/2 of the squared dt. So this dt here is essentially in fact prime function squared again. It gives us dt. So we get the ln of yt should be t minus 1/2 squared t. Exponentiate both sides. So you might look at this and say, all right, well, somehow I played a little bit loose with the rules here, right? I mean, I use this sort of heuristic expression. Do we really trust this? So then what you do is you go ahead and put this expression back into the chain rule to verify it properly. So this is how you really want to play these sort of things. So I would consider this a nonsense for this expression. And you can go back and show how this works. This here is actually called geometric rounding motion. So I think at this point we can take is that we have a calculus that gives us chain product type rules. We know that it all obeys linearity rules. We have some sort of notion of differentials, and we have something for polynomials, which is necessary for the proof, as well as a nice little example to show how stochastic differential equations do not do what you would expect. Because if this were classical, we would not expect this term here. So already we see something strange happening. All right. Other than this, Adrian has some comments he wants to make.
Oh, okay.
Yeah.
Okay, so I take over for a few minutes before the end. So as we define the whole machinery of martingales, martingale brackets, and things like that, we want to use it. So we'll try to see how to define and extend all of this to stochastic control stochastic quantity. Thank you very much. So what we want to define is we take a martingale NT. So we should think of it as volume motion. It's the volume of T, is what you should keep in mind. Then we have some kind of stochastic process, SDEs. And I will not define it completely for the moment. We just get the idea. What we want to define is the integral from 0 to t of x s, d, and s. So x s, d, w, s, basically. So the thing is that we defined it and will not do it because it's exactly the same methodology that Marco showed us. We defined it as the sum of h, ti, no, x, ti, and ti minus 1 is n ti. And you take to the size of the partition minus 1, and then you make a limit when n goes to infinity. I have to say that up till here, this limit was in L2, but in the global generality, what we obtain here is a limit in probability. It's something that I have to mention. We don't care here, but I have to say, because from the point of view of probabilists, this is satisfying, but in the theory of rough path, they hate that. So we try to give a sense point-wise to this limit, which we don't, right? We just have it in probability. We won't talk about it, but this is a very weak limit. Also, you can pick a local martingale, but we just pick a martingale for simplicity. The point is, if you define the martingale like that, you can do the same with step processes, etc. And you obtain three things. So T will process integral from 0 to T of excess dependence is a martingale. This expectation is 0, because we know that for a martingale, the expectation of martingale is the same at all time. So it's the same as its value at point 0, which is 0. All right. And finally, the most important property for us is that if I take two such integrals, dns from 0 to t of ys dnx, I can simplify this with isometry. And that's just one integral of xs, ys, and this thing that we define the variable that we needed now is the martingale bracket of mn. So if you forgot about this thing, I just have to recall that in the case where you have n and t, this is the quadratic variation of that. Okay, so in particular, we have wt is equal to t, right? So when I write, what you should think here is that if you take n is equal to n, is equal to a Brownian motion w. When I write d martingale bracket ww, I just mean dt, but it's this notation that Gianmarco was missing. He always wrote dw squared, and if you want to do it properly, you write d martingale bracket ww. So in particular, if you do that, I can rewrite the properties that we saw today. So for instance, d x1, so just the definition first. If x is the solution an equation of the form f of x equals w, we say that x is a semi-multiple. Is it a true word in English? It's semi-multiple. The point here is this is called the drift part. I call the drift part. The drift part. And this part here, I call it, there are many names, I call it the martingale part. That is, if this part is 0, x, the solution, is the integral of something against w, and is a martingale. So when you say semi-martingale, what you really mean is that you have a martingale part and a deterministic part here. Deterministic. Okay. So if we take x and y as a martingale, semi-martingale, sorry. Then dxy we saw is xt dyt plus yt dxt plus something that is hard to generalize in higher dimension unless we use the martingale bracket and we just this is the one we have s d x y. And the same goes for the chain rule. We have d phi x t phi x of t dt plus 1/2 phi second So if you want to write, this is the probabilistic way to write it. If you want to do probability and use weird notations that mean the same thing as notations analysis, you use this martingale bracket. And the final thing, to prove that all of this is not completely crazy, so we write N2. Is equal to the usual space L2 with respect to omega, the randomness, times 0t the time. We ask that we only take into account progressively measurable function, something that we saw at the very beginning of this part. And we integrate with respect to the measure dp as a product measure dp times d and t. Voilà. S. Then I write h k n2 is all true. So you see, what I want to make here is to introduce this product basically, so that we'll have a norm to work on to, and in the next chapter we'll introduce the notion of continuity. So we want really to create some topology here to be able to make proof and make limits in these kind of spaces. So what we want here is that we have stochastic processes. So we need a usual L2 integral and an expectation of the square of something. So we just define the expectation of the integral from 0 to t of hs s and s. And if you do so, this is the Hilbert space. This is not the space we will consider per se, but I just want to show you that if we use this martingale bracket, we can generalize everything with martingales. And as we saw, a martingale is basically a product function with a different speed. And the speed is exactly controlled by this. So if the speed is, we saw that a martingale can be written as W or indexed by the martingale bracket of M. So basically, you can extend everything by changing the speed of the motion we use. All right, how much time do I have left?
12 minutes.
12 minutes. This is perfect. This way we finish everything with a stochastic integral, and this time we introduce SDEs, examples, and the proof of existence and uniqueness. So the last thing that we talked about and we did not reintroduce, you introduced it also, we just have to introduce a little bit more, is the stratigraphic project. Because if we want to do computations, both in numerical analysis and stochastic differential geometry, we need it. The stratigraphic integral, now it's not hard to find. You write integral of t of x t y t. Okay, the nt. Let's say this is the martingale. Same programming motion again. This is on the LaTeX file is \serve c by rc. This is just a circle. It's quite inconvenient, but no one has anything better, so we use that. And we say that it's a usual integral xt, t, and t, plus the correction term that is exactly what we think of this thing. So it's d, x, and
what is this? Just x and this bracket.
Let's write it. So if m is equal to w, it's a Gaussian motion, and the x of t is equal to f of x plus g of x t into w. Then d xt or dx and t is actually just the martingale part, g of xt, multiplied by dw squared. This is just, it's a weird way of saying I think is fine. I just take what's in front of w here, what's in front of w there, and I put it here with dt. Yeah.
Maybe it's useful to remember this also as the sum. But this is the content.
Especially if we were in high dimension, yes. And the moment that you see that, it's yes, you're right. I like to think of this as something that works in any dimension, but
M is non-random.
Okay, if you take quadratic variation, it's the sum of the squares. The differences. You take the sum of things. You take increment square of the sides. Right? So if you want to do the variation of two things, you take the increments each of them multiply together. That's a square.
let's make an example. So we saw the x. What was your example again? Remember the x equals lambda x dw. Yes. And we saw that x of t is actually equal to exponential lambda wt minus 1 lambda square root 2. Something like that, right? Yeah. Okay. This is annoying because this is not what we want, and the goal of Stochastic integral is to make things natural for the point of view of implementation. So what we do here is that we can say dy equal to lambda yt Stochastic dw. So what this means, let's translate. It means that it's equal to lambda yt dw plus 1/2, and then I take the martingale part of y and w. So I will just take, let me write it properly. So it's just lambda. Nay. Yeah, so that's great. Yeah. Okay. So I add a correction, and if I do that, we can check that one of the get both exponential lambda. So for this particular definition of the integral, we won't study it too much. But basically, if you introduce this correction term, you get the proper differentiation. That is, if you adapt the Ito chain rule, you have d5 of xt by prime of xt. And that's so when you hide in this little circle here is the correction term. And for some applications, including in stochastic geometry, it's easier to consider this. So we will write it from time to time. It's another differentiation. The main problem here is that this definition of the integral is not adapted. So it means that we use definition for the future to define it. Another way to define this integral is to say so we have integral of xt dwt is equal to sum of x dy wti plus 1 minus wti. Now, this is in numerical quadrature method, the method of order 1. Whatever value you take here, it will be of order 1 except for 1. And that's the midpoint method, which is of order 2. It means it approximates the Taylor expansion up to order 2, which is exactly what we're doing here. So the idea of this Stochastic integral is that you replace this by x ti plus 1 minus ti over 2, and wti plus 1 minus w squared. And that's how we define the problem. This is the only change that we have. So here you use not only the information at times ti, so it's not adaptive. This is not a martingale anymore. Its expectation is not 0. All these properties disappear, but you get the chain rule. So you always have to make a choice of what you want. So this one makes sense in probability. This one makes sense in differentiation. And okay, I don't have time to do much more than that. But I just wanted to say that we saw today that to define the integral, basically, we have a choice. We have a choice in the second order term. So I don't have time, right?
You do?
You're fine.
I'm fine. I promise that I will go with it. But I want to talk a little bit about that to finish everything on the stochastic integral. Is that if you want to give a value to an integral of the form f of yt, where yt is a process, think of it as something deterministic, regular, it's fine. But you want to integrate it with respect to dx. And x is a Haldorian function and we say that it's alpha Mendelian, with alpha being between 1 over n and 1 over n plus 1. Then the whole theory of graph path tells you that to define the integral, you make smaller integrals, like in the quadrature formula, you take some, you keep your interval in the middle spaces that will go to 0 in size, and let's say that we have size from 0 to h, and you say that this is approximately equal to f twice 0 multiplied by the integral from 0 to h of txt plus f prime y 0 times f y 0 multiplied by the iterated integral h t x s txt, and then you go on. If you work with, if x is just, xt is just t, then as h goes to 0, this thing goes to 0. Because you have h squared, and you divide by h, so there will be no problem. All these terms will go to 0, and we'll keep only this one. If you work with the stochastic integral, all these terms will go to 0, except these 2 points. And this one has no just value, it's just xh minus x0, right? But this one is completely unclear. And you have to give a value. You have many choices, and that's basically what we do here. When we pick a different term here and there, we choose a value for this iterated integral, where x is w, and this choice leads to Ito or Stratonovich, all different things that we don't use because they're useless. And the whole point of this graph path is that they show that there's always, even if n is greater than 2, it's different, there is always a way to switch from Stratonovich, I mean chain rule, with the geometric graph path to another graph path that is maybe simpler with an Euler approximation that they call branched graph path. And if you look at the works of Martin Eichler and then Kelly, they basically show some trees that there's always a way that uses some Hopf algebra theory to switch from one definition of integral to the other one. And the point here is that there's not only one way to define the integral. Depending on what you do, you want to give to it different properties. And that's also what we do in a simpler way in stochastic. Basically, stochastic integral is the simplest non-trivial integral that disappears. And I will stop here. And next time, we study SDEs.
When you talk about graph path,
Yeah.
what is this? It's just a map, continuous map. So you didn't define it here.
No,
Okay.
I don't have time, but
Yes.
if you want, we can talk about it.
Okay, good. I'm just.
But here, the
all the time you're talking about graph path.
The point is that xt becomes less and less regular. He defined the integral of f1 dxt. So the question is, it's just theory.
Can we think about this like just a cube that is further continuous?
Yeah,
That's
exactly. It's just a curve. It is under continuous. And basically, what we spend the last 2-3 weeks to find a way to understand how to define an integral. And this is a bit weird because for us it's always a Riemann sum. And to think that there are multiple ways to define an integral is not easy. So that's why we spend a lot of time on it. And graph path is basically the whole generalization of this idea in the complexity that is.
I still don't understand. What is the relation between the graph path and the way of interpreting?
Yeah, because so here you replace this by W.
Yeah, okay, great.
Yeah. So W is it satisfies this.
Okay, this is for granted.
It's alpha Mendelian, alpha less than more than 1/2. And what we say is that if you want to define this, you can define it as a sum of iterated integrals. And this one, it's very clear. These ones, they're they will vanish when h goes to 0. And this one is not clear. You have to make a choice here when you define it.
Okay, and it gives us that constructions.
Yeah. Well, that was just the aparte. And now it's time for Kahoot.